Okay, good morning everyone. I'm Marshall Bryn from the GPO, and what we'd like to talk about today is programmable networks in GENI. And we're going to take a slightly different tack, as you'll see in a second. What I'm going to do is I want to frame some introductory comments of what I want to talk about and frame the question. And then we've got 4 speakers who have had experience in working with GENI and programming networks within GENI. So we're going to be having a presentation from Denise Gergen from the University of Houston, from Kiran Nagarata from the Win Lab at Rutgers, from Prasad Kalyam from Ohio State, and from Ashish Vilmiri at the University of Illinois. Each of them will be speaking about their own experiences. And then, time permitting, again, the break and the snacks, I'd like to talk as a group about this topic, about programmable networking in GENI. So specifically, what am I talking about? What do I want to do? Rather than focusing on the technical details of how we do this and how the infrastructure provides it and so on, I want to review from the perspective of the experimenter, who is ultimately the client, the client of the services that GENI is providing. From the perspective of the experimenter, how one can and should be able to control network operations on the data plane that GENI provides. So let's talk about that data plane for a second. You've seen pictures like this before. GENI is fundamentally taking there's a whole bunch of resources that are federated, that are dished up by aggregates, and using the Aggregate Manager API, we're able to gather slices, slivers, and back them into slices, and stitch them together across aggregates, and that gives you a segregated, custom layer 2 data plane topology. That's the idea. So diving down a little bit more. Let's talk about the data plane. We've been talking about what does GENI provide. This is kind of straddling between what GENI provides at the moment, given the experiences that we've had and what GENI capabilities are, and what GENI is expected to be providing in the coming months. But the data plane that GENI provides, I'm going to pick this apart sort of piece by piece. But the goal of GENI, one of the goals, is to provide a data plane to experimenters that is custom, that's segregated, it's layer 2 linked, and deeply programmable. And the focus of this discussion is the deeply programmable piece, but I at least want to get all on the same page about what I mean by these other pieces. By custom, I mean that the experimenter is specifying what they want in terms of resources, what they want in terms of connectivity, whether they want virtual machines, bare metal machines, what kind of how they want it embedded within the physical topology of connectivity, stitched across aggregates as requested and as possible. And there are many different dimensions over which one can specify custom. I can say, I want 2 nodes, or I can say, I want 2 nodes that are across the country, or one that's wired and one that's wireless. You should be able to ask for the kind of topology that you want. And that's what I mean here in the data plane that you're receiving. By segregated, I mean that the traffic between 2 different slices are kept separate. My traffic doesn't touch your traffic. You have, for all intents and purposes, you feel like you've got your own data plane that is independent. That's traffic segregation. Your traffic can't enter my slice and vice versa, except by special mutual agreement where you sort of bore a hole between them and allow special traffic to go through by sort of out-of-band means. And we expect to use VLAN tags as the segregation mechanism. There are other ways to do this, but we expect that the GENI topology, the way that GENI is going to be providing the data plane, will be using VLAN tags as that segregation mechanism and as the stitching mechanism. Now, that's going to require, at points as we do the stitching, it's going to require some VLAN translation, some management of limited VLAN tag resources. It may also impose some limitations, which we'll talk about in a little bit, on the experimenter. If this is the way that we're going to be doing that, building that data plane, one of the limitations we're going to be putting on the experiment is you can't mess with the VLAN tag in the frame headers. When we talk about segregation, people usually think we're talking about the implication is performance isolation. In general, GENI does not make performance isolation assurances. But there are some resources that you can go and get some computation resources, some network resources that allow you to make such assurances. It's not in general something that GENI provides, but it really depends sort of aggregate by aggregate. Layer 2 linked. The data plane is a layer 2 data plane. It's a layer 2 network between the compute nodes as specified in the RSpec. It isn't necessarily one broadcast domain. It's typically sort of a point-to-point domain capability. There also, typically, you're going to be getting a layer 3 control plane access to the compute nodes in order for you to get in, to SSH into the nodes that you get. Either they will have public-facing IP addresses, or the aggregate itself provides some sort of SSH proxy so that you can get in independent of the data plane. So this is how you get in, you set up your experiment, but the data all flows over these interfaces. This is all by way of introduction. So now, given that data plane, one of the goals of GENI is that it be deeply programmable. What we mean by that is that you should be able to program, to manipulate, to assert all the details of the network operations on that data plane. The way that that routing decisions are made, editing frames, creating entirely new protocols above layer 2, any kind of layer 3, layer 4 protocols you want. You ought to be able to do that. And as I say, it's this aspect that I really want to focus on in this session. Okay, so where does this happen? What does it mean to be programming the network? There are many different places where this could be happening. You're given a data plane, and the data plane consists of a number of compute nodes, a number of physical switches along the way, and there's also software switches along the way. These are going to be, especially in the case where you've got virtual machines, there's going to be software switches that connect the hypervisor in with the rest of the hardware. And so you've got physical switches, you've got software switches. The GENI racks, we expect that the campuses, at the regionals, at the backbones, that they will contain an OpenFlow switch. We understand that currently OpenFlow support across switch vendors is uneven. So there may be limitations of what you actually get, and we need to understand these things. There are some that claim to provide hybrid mode, where you can have one port that's OpenFlow enabled and another that's not OpenFlow enabled. This is a perfect example of uneven OpenFlow support. This would be a really nice capability if it were available, but it's not uniformly available. On the software switch side, there's often, if you're dealing with Linux environments, OVS, Open Virtual Switch, is provided standard in most recent Linux distributions. And within that, you can write your own modules, write your own protocols. It also, an OpenFlow software switch is provided within OVS so that you can write a controller for networking at every node. I forget when GENI in a box was. That today? Is that today or is it yesterday? But it's today. We're going to be demonstrating this new GENI in a box capability, and it uses OVS to construct its own topologies. And Zorp and Click are other popular software switches. These are all ways that people have and will continue to be able to program the network. So, looking at this from another dimension, you can apply these different approaches. What do we mean by programming the network? Well, you can establish rules for the way that frames, and I'm talking about frames here, not packets, because we're really down at the layer 2 level. You could establish rules for how frames are going to be handled. You can set up flow space rules in FlowVisor. You can set up routing tables in the kernel tables. You can set flow mod rules in the OpenFlow switch that determine how, given a frame with particular criteria that match, we want it to go out this port. You can also have in-the-loop frame handling. An OpenFlow controller can take every single frame and say, well, if it's this, then change this part of the header, go out this way. It provides fine-grained control. Now, obviously, this is software in the loop. It's not efficient to do that, but there are certain experiments for which you're not worried about performance. You're worried about testing out an algorithm, making sure that things work. So you can do this. There's also encapsulation, tunneling approaches that one can, given the data plane, build those kind of connections on top of what you're given. And as I've said, it's possible to implement non-IP layer 3 protocols, given what you've got in the data plane. The data plane is yours to program, yours to do with what you can and what you want. So, from an experimenter's point of view, it should seem that what you're given in the data plane is a local area network. Now, in fact, it's a wide area local area network, which is to say, you often You know, it's different from just setting up 3 computers in your lab. We understand that this is going over if that's what you asked for, over the whole country. It could also be a series of LANs. If, depending on the topology that you've asked for, every node can have multiple interfaces, so that you can have complex topologies where these guys can talk and these guys can talk and they can only talk, and between them there's one link between them, if that's what you asked for. Which nodes can communicate with which nodes over which interfaces. In the data plane, what you're getting, there may be a lot of different pieces that aren't visible to you. That aren't visible to you as an experiment. There are intermediate hops that may be tunneled, or for whatever reason, there are hops that aren't at GENI nodes, so that you're not either going to be able to see them, or certainly not going to be able to program them. You may not be able to install your controller at certain hops along the way. So, you know, those are sort of the facts of life of what you've got. But the parts that you can see and the parts that you can program are yours. I mentioned this before, there are likely to be some restrictions on what you can do with the layer 2 headers, specifically with regard to changing VLAN tags. If we're using the VLAN in order to slice the network and stitch things and do the segregation, we're going to be requiring that, you know, that part is hands-off. And as I mentioned before, there may be limits on layer 2 broadcast as opposed to point-to-point connectivity. So, this is all by means of introduction. I really want to focus this session on the experimenter's experience. So we have 4 different speakers who have worked on aspects of programming the network in the GENI context. So I'd like the speakers to talk about their experiences and particularly focus on a couple of topics that I think will help to drive a good conversation afterwards. I'd like people to talk to what the experimenters have been able to do in terms of network programming on the GENI data plane. What have you been able to do, and specifically, what's been easy about it? What's been hard about it? What is your experience of trying to do that been? Given that, if GENI could add some capabilities, some support, some tools, what future capabilities would make it easier to support you in your desire to do network programming? Are there some graphical tools, some topology, some path services? What is it that was hard that would make it easier to be able to program the network, and not only to program it, but to know how it's performing in the experiments that you've put together. So, you know, GENI provides a lot of different capabilities beyond just data plane provisioning. There's authorization and authentication, logging and monitoring. There's all kinds of things. From a federation or a GMOC level, are there something that would help you to analyze what is happening on your experiment that we can provide that would make it easier to build the experiment, run the experiment, analyze the experiment? These are things that we really want to be able to understand and help the experimenter community with. So, the goal of this session is really, I'd like to have the speakers come and give their experiences and their opinions and then hopefully before 9:45, I'd like to open up the conversation to people who are interested in doing network programming within GENI, what their experiences have been and what their desires would be, because we're looking for some guidance here. It's really the experimenters that drive a lot of the priorities and, of how things develop within GENI. Okay, before we bring up the speakers, any questions, any comments? Great. Okay, our first speaker is Denise Gergen from University of Houston.
I have been involved in GENI from an infrastructure building point of view for a while now. We have participated in stitching VLANs across from RANSI to Texas through multiple regional optical networks, and we ran some very basic layer 2 connectivity experiments during previous GENI conferences. Now I'm trying to go to the next step and run programmable networking experiments on GENI. And I would like to share with you some of the experiences that I have now coming from some demand coming from industry. And I think by voicing these here, maybe I can help us just think about ways that we can have the GENI experimentation as streamlined as possible, particularly for creating almost like a research and development lab on GENI as a live testbed. So I do applied research. Let's say if a new concept comes in programmable networking, and if I would like to do test validation and enabling of research using a real-life network, GENI is the perfect place. But in order to realize these, we have to create some benchmarking methods on GENI that's applicable to GENI capabilities. And I'm still looking forward to the time when we will have opt-in users on GENI testbed, where while these protocols or products, etc., are running on GENI, there would be opt-in users that are using the infrastructure. Little bit of information about myself. I have only master's students that I can advise in project and thesis. You can imagine they would like to graduate within 2 years. So the learning curve has to be really fast in that sense. They need to be able to come up with a hypothesis and learn about GENI capabilities, and then deploy their experiments on GENI, take test and measurement, update hypothesis, and come back and immediately graduate, and then hopefully find a great job. So that's my goal. That's the overlapping interest, and GENI is so far able to give me such a capability. And I'm teaching classes as well in graduate level and senior computer networking class. And I'm actually using GENI platform in senior computer networking class and graduate level courses, which just started. So these are the sample of classes that I teach, and all of them are applicable to running experiments on the GENI platform. So this semester I started assigning projects to network programming class with GENI in mind. And these are the topics that came up with the teams. And we are halfway into the semester, so they may actually end up getting deployed on GENI. I'm hopeful. We actually took configuration examples from Open vSwitch. For example, congestion monitoring leading to some kind of active networking. OF config is another one that came as a standard from the ONF. And there has been discussion about management versus control plane inside the team of students. We have another team working on network connectivity in SDN. We are trying to redefine what connectivity means because there are so many protocols involved in enabling a connection of a host or a service, or which level do we define the connectivity, and what does it mean in SDN? Another project was hop limited flooding. How can we implement such a scheme in an open flow network is now being considered in the team. There is one on VLANs for VMs. Can we do something like that in a very streamlined fashion instead of going into the hypervisor and configuring it? And I'm noticing that this can be done on GENI in a very streamlined fashion. We just have to get there with the students' knowledge. So this is a snapshot of what I have as resources for my students. How do they set up the projects? And then we have virtualization through just VMware Workstation on students' PCs, and a computer lab equipped with VMware Workstation on each computer. We have OpenFlow tutorial with the Mininet, the classical tutorial. That has been extremely helpful in explaining what we mean by programmability, and that actually gives us the way towards GENI very, very quickly and very easily. Zen server with OVS and configuration point considerations for the management plane are another resource that I have in my lab. So, all of these, as I said, we are halfway into the semester. Hopefully we'll go into GENI. So just want to give you 2 slides here to my impression of, okay, how do I set up an experiment on GENI? What is my thought process? So I would like to use exogeny racks because bare metal or VMs are possible, and custom VMs are relatively easy to create. So user certificates, okay, we have done this before. How do I modify my images? It's actually clear. Intra-rack slicing is a good thing to have because I might try within one rack, whatever experiments I have, and then expand to wide area. The ultimate goal is going to be the inter-rack slicing and open flow. So it all seems reasonably outlined in the wiki of exogeny. The tutorial yesterday was wonderful in explaining all of these to us as well. One thing we have learned yesterday was, I just wanted to explain to you, again, my thought process is that I can possibly deploy my controller on a slice that I create and then point to that in another slice as the controller for the OpenFlow network I'm going to create in the secondary slice. So I don't even have to host my own controller, it seems like. So that's very good to know. So with these in mind, let me go through what I understand from programmability, and then I will give you 2 example programmable experiments that I'm planning to conduct on GENI. So what I understand from programmability, I would be able to change, configure, provision, and then manipulate the network. This can be the logical topology, code of service, path computation and assignment, and then these can be constrained by the application and service requirements against congestion. Security is a big concern, mobility, VM migration. I'm just giving you some keywords on what I understand from programmability capabilities. And then the resources on the network, how I measure the performance of my experiment are, of course, other constraints. The main things in my thought process are, okay, I need to experiment within a virtualized lab resources first in my own lab, and then I need to be able to create custom VMs. One question that comes to my mind is it possible to put custom network devices inline into the GENI infrastructure, given there is a great push by industry to use GENI platform as a test bed that might be coming up soon. So here are my 2 sample experiments. The first one is an emergency management scenario. Sorry. Let's say the main purpose under that scenario is I would like to achieve dynamic network provisioning to enable emergency applications experience high quality transmission on the network. During an emergency, I would like my video feeds from IP-enabled video cameras around the buildings to go to police officers' handheld devices at high quality. I would like to prioritize the network without going through all the configuration steps that network engineers now do. The hypothesis, as you can see, is a little bit shaky. It's not really a very scientific hypothesis at this time. It's going to get refined as I deploy this experiment on GENI. I'm just claiming that automated application layer network provisioning will help emergency management achieve faster information retrieval, because The reason I say shaky is because, okay, they can get information faster, but is that going to help them make decisions faster as well? Because as they get more information, even more information is desired. I'm not sure how to explain that, but as soon as more information is provided, maybe some analytics will play a role as well in making decisions faster. So, all right, good enough. So plan of experiment, let's say we would like to compare the overhead in network provisioning and setup with the time scale of a typical network engineer initiated configuration workflow. Measuring this is very, very difficult. That's why I put down reservations. Metrics for measurements are not very well defined. And it's going to depend on what measurements are possible on GENI, what measurements I can design and deploy on GENI. And while I'm designing this, I might make mistakes in what measurements are required for this particular hypothesis as well. And another reservation I have is the just proving the claim means maybe I need to have the slices to have multiple paths between the same endpoints so that I can show that my automated network provisioning worked. If there's only one path, then it will be very difficult to make a claim like this because everything is going to flow on that path anyway, so what's the point? Or is there any role of the management plane in this whole setup? Because if going back to my plan of experiment, how do I compare this time scale of typical network provisioning done in this kind of a situation? So these are the reservations I have. Again, a little bit shaky in argument, but that's how. By the way, these steps that I'm outlining here are taken from the experimenters' session yesterday, and that actually seemed like a very good way to start designing an experiment. So what are my necessary resources to get started with this experiment? I need VMs with applications to generate the traffic. And I need to host the emergency management application on these VMs as well. Multiple paths, possibly. And OpenFlow controller so that I can have my capability of pushing flows or changing priorities and monitoring quality of service. And of course, very, very important measurements. So that I can try to test my claim and then update my hypothesis. Another experiment, the second experiment I have in here is programmable network nodes. We demonstrated this during the demo session on Tuesday. The purpose is to create applications that would actually run on network nodes instead of the endpoints. The motivation of such a box was we teach network programming by using endpoints. Open a socket, have client server, and then write an application that will run on the network, but it will not really program the network. It will program the application itself, how it behaves, and given the network. So what if we had a capability that network nodes themselves would have applications that are running on them? How would that change the way we realize networking? One hypothesis, well, if we have an application that performs TCP SYN attack detection, would that be more effective than the endpoint counterpart of such a scheme? And there was a paper published by Xflow research guys, it's on their website, that actually supports this claim. And I would like to realize this experiment to measure and verify. So plan of experiment would be run various scenarios, some topologies with multiple paths, with the same attack destination, with attacks, and then detect at the end point and intermediate nodes and measure the time to detection, effectiveness of detection, etc. You can put there. Again, my reservations in this experiment setup, metrics for measurement are not very well defined because, again, I don't know if GENI has the measurement capabilities that I need for this, or I don't know if I can program the measurements effectively to measure exactly what I'm looking for. But as I deploy, I'm expecting these will become clear. The attack applications may be too obvious. I might not be able to create the scenario very effectively. So that's not necessarily a shortcoming of GENI, but it's just the way it is. And how can I insert a new hardware into the GENI infrastructure for this experiment? Not that I absolutely need it in the infrastructure itself. Maybe I can get away with putting this hardware on the edge. But this is a new hardware, as I said before. So how is that going to affect the design? Not sure. So again, necessary resources that are in my mind are VMs with applications to generate this attack. I need to deploy an endpoint detection app so that I can compare endpoint versus inside this node detection, OpenFlow controller, and then measurements. Of course, these are going to be defined as the resources are allocated. So these are the two experiments I have in my mind. That's all I have. Any questions?
So you'd like to stick this new hardware in local resources, or you'd like to send it to like somebody else and have it put in multiple places, or what?
I can try both. Yeah.
Do you mention?
I'm not sure I have an answer for that.
Yeah, I know. I am thinking exactly the same thing. I'm not sure if it will prove the point by putting it on the edge. But maybe I will have an island in my site that will attach to GENI for just the experiment duration, and then that island will serve as enough of an edge. So.
Right. So for example, if you could plug this, let's say, for example, that you had an ExoGENI rack, and you could plug this into your ExoGENI rack and force all traffic from your slice to go through that device before it actually hits the node.
That's one of the thoughts I have, exactly, yeah.
Yeah, okay. I mean, so in the InstaGENI racks, we kind of have a story for this, but nobody has tried it, and so right, we kind of have this. We have a way that you can plug stuff in, and a local administrator can say, okay, here's, I can enter some information about that thing so that we can make VLANs to and from it.
Okay. I'm expecting in the future there will be these kind of products and nodes that might need to be hooked up, or measurement devices. Actually, when we first started 5 years ago, there was a talk about can there be external measurement devices that we can host on GENI nodes. So.
Yeah, and I mean, and I assume that I assume it would be acceptable to you if this device itself was considered by GENI to be kind of an external thing, that it just knows how to make a VLAN to, but it's not trying to do any provisioning
exactly.
on the thing itself.
Yes.
Yeah. Okay.
Yeah, that would be acceptable.
Do you see a transition path from software switches to hardware switches in being able to deploy something in software and seeing that it works, and then?
Yes, definitely. Yeah.
Yeah, so I'd be kind of interested in trying this if you're able to, I mean, you guys have or are getting an ExoGENI.
Yes,
So
we
maybe
already
should,
have
so
one.
maybe, okay, so maybe we should work with that first. But if you can't get that to work, I would be kind of interested to try to figure out how to make this work. If you can.
Yeah, we can go in parallel. That's yeah. All right.
Thanks, Denise.
Hi, I'm Kiran Nagaraja, and I'm from WinLab, Rutgers University. So I'm a researcher at WinLab, specifically working on the Mobility First project. As some of you might know, Mobility First is one of 4 future internet architecture projects sponsored by NSF. I mean, obviously, Mobility First is a broader project. Multiple universities are involved, led by Rutgers University. So it's a fairly large project. There's prototyping work that's going on in the individual projects, but we also are trying to build a project-wide prototype, a platform where protocols can be evaluated and validated. And so GENI is one platform, testbed for evaluating these protocols. So what we see different about GENI is that obviously we could run all of these experiments in a smaller scale within, say, things like Emulab locally or Orbit testbed within WinLab. But with GENI, I think one aspect is the realism in terms of the wide area deployment. And not having to actually emulate the latencies or the resources that you might see on a wide area network. So what I'm going to do is try and provide some background as to what are the kinds of things that we're trying to evaluate on GENI, and then look at the specific experiments that we ran and how we're using the programmability within GENI to enable some of this validation. So before that, I think the first speaker did a great job, looking at, if you're trying to use the platform as an instructive platform, engage students to run experiments and so on, there needs to be certain, addressing of the learning curve, the tools that you're provided, as well as the hardware infrastructure and the capabilities and so on. But I'm going to try and dive directly into the protocols that we're trying to evaluate and the specific experiments and some topologies that we've looked at in GENI. So this is a sort of a common mobility scenario or mobility first scenario that we're looking at, which is essentially in the future there's going to be an increased number of wireless devices, much more than wireline devices. So we're tackling the future internet architecture design, with mobility as the primary and intrinsic property at the network level, right? So within WinLab, there's research which spans a broad level of issues, all the way from the physical layer up to the application layer. But within the Mobility First FIA, we're looking at network level protocol design as the primary focus. So the network scenario that we're looking at is, there is a core network. Obviously, it's not this simplified. There's going to be multiple networks, interdomain components within the core network. But there's also going to be these wireless edges, access networks, which plug into the core network itself. And so mobility will be the norm. Devices move, content moves. The way you describe a context, which might be addressable at the network level, will be changing dynamically. So devices will have access to heterogeneous networks. Devices might be multi-homed, connecting to multiple networks at any point in time. So whether these be cellular, 4G, Wi-Fi, WiMAX, all of these networks are something that we want to consider as part of the access networks. And the device being able to move freely across these things are of primary concern. So we're also looking at things like disconnections, what happens during disconnection. You might also see aggregation of multiple of these devices into ad hoc networks, which might then plug into regular operators or ISPs on a dynamic basis and plug into a routable global network. So with all these considerations in mind, so we came up with the mobility first architecture. I'll spend a couple of slides on just describing the key parts of the architecture that we're trying to validate on GENI. So the primary aspect of mobility first was we try a clean separation between the name and the network address or the locator. We introduce another naming layer or a layer in between, which we call essentially every end host will have a globally unique identifier, a GUID. So how this GUID is derived will depend on certain intrinsic properties that we want to ensure that the endpoint will be able to provide. So for example, all hosts may be given a private key, which then will decide what the GUID is. So for example, the mobility first protocol, the implementations that we are presently looking at will have a 160-bit GUID, which is derived as a cryptographic hash from the public key of the entity itself. So when we're looking at mobility at scale and want to be able to support mobility at scale, we're thinking of this being supported through a global name resolution service, which could potentially be tightly integrated with the routing fabric itself. So the global name resolution service will map the GUID of any endpoint network attached object to the present locator of the object. We're also looking at routing fabric which understands both or is capable of doing both GUID-based routing as well as address-based routing. So GUID-based routing, when we consider it to be a completely flat network, this we are thinking of applicable in a sort of a limited scale local area networks, intra-domain type of environments. But also, we allow the routers as well as endpoints to be able to do dynamic resolutions to determine what is the current network address associated with a particular GUID. So another key aspect of the mobility first routing fabric is the ability to be able to buffer or hold packets. If there are conditions where the end host is either disconnected or the path quality itself has degraded temporarily. So we envision routers either at the access networks or in some cases deployed as co-located services within the core network itself to be able to buffer or hold packets during transmission. So finally, another key aspect is that we see these networks to be flexible, to be able to deploy new services in a very easy incremental fashion. And in order to enable this, we provide for a compute layer plugin to the routing fabric that can then be invoked by the end host or by the routing fabric itself. So you could imagine this to be data centers or clouds to be plugged in directly into the network itself. So just a brief overview of the protocol stack, and this will define how we implement our protocols and evaluate our protocols. The key difference between the IP or the OSI present architectures is that the narrow waist is now based on a GUID rather than an IP address. So the GUID enables both registering of the GUID of the endpoint with the network, associating with the network, as well as the resolution of the GUID to the network locator dynamically to determine where the mobile node or network attached object is currently resident, right? So there are also other components such as the storage aware routing, inter-domain routing components that we want to evaluate on the GENI platform. Right, so and along the control plane, we have the GNRS component, which provides the name resolution. So we have prototype implementations of these different components. And in particular, we have a click modular router implementation of the protocol stack, as well as end hosts implemented on Android and Linux clients. So currently, we're pushing for a very large-scale evaluation of the GNRS, wherein the name resolution is tightly integrated with the routing fabric. The router can actually invoke a resolution on a packet that arrives with just a GUID, or there is a routing failure and needs to be re-resolved to the latest locator. So I'll dive into some of the experiments, and actually, so this is sort of twofold. One is, we wanted to run our protocols, whether it's name resolution or the routing protocols itself, on a wide area network which has both wired and wireline components to it. The second aspect, so in this particular section, it's more about how do you put these different network components together to be able to have an edge core edge kind of topology that can then help validation of end-to-end protocols, including wired and wireline components. In the second aspect, we actually want to introduce programmability to enable protocol implementation itself. So in the first aspect, so mobility first, the routing protocols could either be implemented as distributed services, or they could be implemented in a SDN type network where some of this control is centralized. So we're exploring both of these approaches. That is, mobility first can be implemented as this distributed routing control plane and network support services such as GNRS, or they could be implemented in a centralized fashion within SDN type segments. So in this particular case, so we're trying to integrate the wireless components with the wired. So this is a topology that we thought about for validation of multi-homing feature within Mobility First, wherein a client would connect to two different types of access networks, WiMAX and Wi-Fi, and also storage-aware routing, wherein we could disconnect some of these or degrade the link quality to these access networks. And the routers within the core or the access networks could then buffer the data that's being transferred to the endpoints. So one way to think about this mapping between what the experimenter thinks about as a topology and the testbed facilities might be that you sort of map the US map and the GENI resource availability across this and say NA1 could map to Stanford, NA3 could map to Utah, NA5 could map to Chicago, NA6 could map to New York, and so on, right? So that's one way to go about it. And I think that would be relatively easy for a programmer or an experimenter to think about, in terms of the GENI resources, especially if we have resources distributed across the nation. Then that might be, a direct way of mapping things for the experimenter, right? So, so what we did is obviously, so there are some limitations. Things are being improved. The wireless components or these edge networks are present in various sites, various universities. WinLab has them, and Wisconsin, UMass Amherst, all have deployments of WiMAX and Wi-Fi capabilities, but integration into the core is another question, right? And slowly that's being addressed, and I think more WiMAX sites are coming online now. But we had limited options in terms of what we could try, so we chose BBN, who's always ready to help out the experimenters in trying to set up, whatever we ask them to. So we use BBN and WinLab as two wireless edges, and then use the GENI backbone and Proto-GENI host deployments as the core network, which we then split up into all of these individual, networks. So if you've seen the netcore topology of the Proto-GENI deployment, and so there's essentially two, and I think now there's 3 different VLANs which actually interconnect in slightly different permutation of the four, is it 4 or 5? 5 NLR switches and 4 I2 switches so it's probably 5 of each, and maybe there's more updates now. But essentially, one VLAN would connect these switches in one order, and a different VLAN would connect these switches in a different order. So we went to BBN with this topology, and what we wanted was an isolation of these two different paths until the point that they actually reach the core, right? So what we wanted to try out is if we have a routing fabric which can distinguish between these multiple networks and also determine what's the access quality here, then you could actually dynamically do multipath, multi-homing, and determine what's the best delivery point for these endpoints. So we wanted isolation between these two paths as we set up the topology. But you can see that it's already a mishmash from this clean topology that we had to what we're getting at in terms of the physical topology. But this is fine. I think for people who already are wrapped up on what's the topology, what are the hardware resources underneath, how do VLANs function, and how can you actually stitch together VLANs, this is still workable, I think, right? But the next thing is we also want to introduce students to get onto these networks and platforms and be able to start programming or validating mobility first protocols. So this view actually looks much more favorable or easier to ramp up on than this view, right? So some of the maybe it's part of the visualization tools, maybe it's tools to stitch together topologies based on the requirements of the programmer could potentially help how these things reduce the learning curve for new students to get in and start programming. So essentially we chose a spatter of these end hosts or points to use the protogeny nodes at these things, at these sites to deploy mobility first routers and name resolution services. And as I said, BBN and Rutgers were the two edge nodes. So this was fine. So we actually ended up using, I think it's 3716 as the VLAN across the NLR switches, and 3715 across the I2 switches. But what we wanted was actually a bridging of these two VLANs at the core of the network, right? So this gets to what Brian was pointing out in terms of the VLAN translation and bridging. That could be beneficial, especially when you're going across different aggregates. So we actually ran a click router here to be able to do this bridging. But that's, I think that's another thing that needs to be, where the experimenter can get some help in setting these things up. So if you have these custom requirements in terms of being able to isolate different parts and so on, and then you eventually want to stitch together these different segments of the network, then VLAN bridging and translation can really help. So we set up content publishers and content subscribers at the edges, and were able to demonstrate the storage-aware routing concepts as well as the multipath, multi-homing abilities within the mobility first protocol. Right. So get into the second part of the experimenter's viewpoint from mobility first. So until now, what we saw was using the programmability in terms of setting up VLANs, in terms of setting up topology. So we also used a custom, layer 2 ether type for mobility first, and all of this was enforced by the OpenFlow switches within the GENI core. So the second aspect is we actually want to use the deprogrammability to control how the flows itself in the data plane would be routed or forwarded. So in this particular experiment, so what we're considering here is segments of the network which might be OpenFlow or SDN type, wherein you might have centralized controllers which then put in the flow rules to the dumb edge switches to determine how flows are forwarded. So the topology here is a simple one, and we actually did this on one of the sandboxes of the Orbit testbed. And I'd encourage people to take a look at it because it gives a lot of flexibility in terms of how you configure programmability on this particular OpenFlow switch. So here we actually ran OVS, but we used OpenFlow enabled Pronto switch to connect all of the different nodes together to be able to enforce the topology across across the different nodes. Right. So the Pronto switch was actually running Never mind. So I'll actually get into the description of the protocol as to what we're doing with the OpenFlow switches itself. So we wanted to demonstrate the buffering ability of the Mobility First protocol. So if you have end hosts connected to this OpenFlow segment, then if there is disconnection or migration, you can think of this as either a wireless node disconnecting, or within data centers, you have migration of VMs or end hosts and so on. So if there is a disconnection, then the flow or the data packet can actually be buffered within the network. In order to do this, the controller maintains status information about who's connected on what port on what particular switch, and if there was a disconnection, the flow would be marked and routed to a storage component wherein it would be buffered, and as soon as the node comes online, we pushed it down. So in order to do this, we actually had to do header rewrites on the switch itself. So that's something that we've spoken to a few people in the last couple of weeks, last couple of days, and that might be a limitation within the OpenFlow deployment within the GENI core and the edge at this point. But it would be nice, and I understand Brian's point about different switches having different capabilities and so on. But it would be nice to have that complete flexibility in terms of being able to change headers or even getting up to the later versions of OpenFlow features. Right, so another thing that we tried out here on the Sandbox 9 of the Orbit was migration itself. So we, all of these nodes run on VMs, and we migrated nodes from one OVS to another OVS so that we can also be able to demonstrate the ability to handle mobility. Migration of VMs, I think, though it's not a programmability aspect, I think that's something that would be a useful tool as well on the GENI platform. So to summarize, without making very broad conclusions, I would say one of the key things for Mobility First is that these wireless edges need to be integrated into the core so that we can run multi-site experiments which involve edge core, edge topologies. And I believe sitting through the WiMAX status updates, so we see more of these WiMAX sites coming online. And that's good, and small experiments have been run, which is multi-site across the WiMAX things. So which is becoming more programmable in terms of how these networks can be included and code deployed at these endpoints. So VLAN. So in terms of the programmability, I would say the VLAN translations and bridging, as well as more flexibility or advanced features or later features of OpenFlow within the OpenFlow switches in the GENI core, I think would be a useful addition. So if you need more information on Mobility First, you should be able to find it on WinLab's site, but you could quickly search it. So any questions?
Great, thanks a lot.
So, good morning. I was trying to figure out how best to sort of organize the presentation, and sort of what I came up with is defining, at least identifying some of the capabilities and needs we need for our experiments, and essentially things we are doing in VM Lab, which is the link is provided there, which is funded by NSF, and we've been doing sort of experiments connecting VM Lab to GENI to EmuLab and other places, and so sort of building an extended test bed. So I wanted to sort of motivate our capabilities and needs, not really to say what is working, what's not working, but really to kind of outline the issues that we have sort of faced, overcome sometimes, maybe still struggling with, but I would just sort of lay it out as requirements, and then hopefully that will initiate a discussion. So the requirements, I have sort of 3 projects that are sort of related, but have a direct significance for using SDNs or OpenFlow in our experiments. One is the VD Cloud experiment that I talked yesterday in the plenary, and also the VDCCM I talked yesterday. That is more sort of an educational tool also that we're trying to develop. And the latest is the CCNIE award to build science DMZs between different universities and connecting them via wide area using some of the programmable networks. So those are sort of interesting things we want to do in the future, so I wanted to sort of bring that into the conversation. And I presented this a variant of this yesterday. So we're basically working on taking our VMLab data center. It's all sort of VMware based, trying to mirror that at EmuLab. So basically install ESXi VDI tools and have VMware view clients and our sort of software that will instrument, and also software that sort of takes these requests as they come in and applies different resource allocation schemes for provisioning resources, placing them at different locations, and doing some optimization. So and so we look at things such as load balancing. We're interested in benchmarking thin client performance over wide area. We're interested in looking at the impact of applications within virtual desktops at different system loads, network health bottlenecks. And so one of the things we did was, like Kiran was explaining, so there is this nice sort of path switching capability at Rutgers, where there is a path that I could take from Rutgers out to GENI and other wide area destinations that goes through a sort of an isolated OpenFlow path. And then there is another path, that's sort of the internet path. And here, I think I switched it. So this is from the wiki. You can see that sort of that path is much more cleaner getting out and is sort of all layer 2, whereas the internet path is sort of going through the enterprise campus core network and sort of going through firewalls, and so it's all sort of layer 3 connections. So this is sort of a very rich setup at Rutgers. So we tried to utilize it for our experiments to see if that makes a difference within virtual desktops. And so we sort of looked at the latency throughputs, and there is a little bit of a difference. It's not significant, but definitely we could sort of see the effect of that within the application. happens when all of these people are using these different applications, and the resources in a cloud for a virtual desktop is much larger than a sort of a Amazon transactional database kind of a thing, right? So you're giving an actual desktop with 2 gigahertz CPU, 2 GB RAM, and so you're providing a lot of resources. So how you can tune them and how the impact of the tuning affects user experience is sort of not well studied. So to do those things, definitely large scale traffic handling and controllers sort of not crashing. We've had some of those cases, and maybe it's just our configuration, but some robust controllers are key. And obviously easier management, debugging of flows, better tools. We do a lot of log analysis. There'll be a easier path with their better visualization and analysis tools. And in the same sort of line of thought, more visibility of bandwidth consumption of flows, flow tracking, easier configuration, ability to add, delete flows, interface configurations, and also sampling different kinds of things from the interfaces. And Sudarshan put this up in terms of access to MAC address tables for debugging. He found that very useful. And also the other thing he was sort of struggling with was he creates a slice and then he does some work, and again he wants to capture that state, and when a new slice gets set up or he wants to extend this slice, sort of importing, exporting configurations, he felt that that would be great to have. And going on to the next topic, I kind of talked to you about this idea of a simulator we could basically use for our research as well as for some educational purposes. So there's a button, you can run some simulations, and also you can sort of press another button and configure it to actually run a real GENI experiment. You can see how the allocations happen, how the net utility is changing, and I kind of give you this example of a roller coaster design game where you could get points. So sort of building on that, a little more details. So we're working with Sonia Fahmi's group to sort of get some courseware based on our experiment that could be posted on the GENI wiki, and hopefully we can help somebody run a class with it. And one of the things is really looking at this net utility score and saying, challenging the students to say, if you get more than a 30 plus net utility using some intelligent adaptations, you get an A grade, and you're in trouble if you're only getting 0 to 20 net utility. And how you could encourage them to learn and do it is obviously get into GENI, set up some of the slices and work with some of the tools, experimental tools, and really look at the science there, right? Compare schemes of current practices. If you need a desktop, you basically just go buy the best desktop available in the market, but that's expensive. That might work for your father who's just browsing email, but your brother who's doing gaming, he might complain it's not a good desktop. So you need to sort of do a utility directed allocation versus just fixed provisioning that we do today. So they could compare that. They could compare again, should you place the desktop closer to the user on a least load or a least cost machine, or is it a joint? So they could try these different optimizations and see what's the net utility that's derived, and probably improve the net utility by different adaptations in this client, in the server, and using OpenFlow in the network, right? So if they can bump up their score as much using some interesting adaptations, they get a better grade. So that would probably a good course. I don't know. We'll see. But what if we ran that course? What would be the sort of infrastructure that's needed? So definitely in GENI we need all what we need to do the experiments, which I listed out earlier. And if we think about a scenario where a TA sets up this slice and he's giving these multiple controllers to be used on the same resources to sort of run their examples and experiments. So that would be an interesting scenario. I don't know what will be the problems, but I imagine that's the scenario. And obviously we need good documentation so that students and others are able to, in a very short time frame, like Dennis was saying, pick it up and actually get some real work done. And other challenges we'll know when we try it. So we haven't tried it yet. And the last use case is the science DMZ use case. So this is, I think, from my perspective, one of the most exciting projects we'll be working on for the next 2 years. And so the challenge at Ohio State, and very well was sort of described in the CCNIE program, is a lot of the researchers have big data needs in astronomy, psychology, brain imaging. I mean, there's so many diverse areas. We made a survey, and all the physics is sort of the biggest end user, and they all complained that they could not control the policy of the networks. So the networks in the campus at the edge, and OSU's network is pretty big. All of it was set up for security. It was very secure and enterprise ready, but in terms of performance, it was really not good for science. And so they always wanted a high performance sort of edge network, also a way to apply their policy on what research data sets they want to get, what ports had to be opened. So they wanted this sort of a control on the network that the enterprise engineers never gave. And so we recognize that there are systems engineers and network engineers on campuses, but there are no performance engineers on campus, who are the kind of people who would sort of look at the user, look at the resources, talk to the engineers, and these are roles in Akamai and other places, but not on campuses. So how about we have a campus engineer operate a science DMZ with some of the OpenFlow equipment, personnel equipment, high capable data transfer nodes, and some policy directories and servers, and link up the network in a DMZ that would connect back to GENI, or for example, DOE has a lot of the facilities that are OpenFlow capable, and NSF has a lot of resources that are capable. DoD has resources that are capable. So all the edge sites are doing it, all the sort of the remote sites or instrumentation sites are doing it. So how about we link up the last mile at the campus to do that? And also, if there were universities to university science DMZs, and so this is the case where we have a mirror DMZ at University of Missouri at Columbia, and again, researchers in both the universities trying to do some big data experiments in brain imaging and soybeans. How can we sort of use GENI as a testbed to try some things and then put it on internet too? And so that's what I've captured here. So we want to do some experiments across different campuses, federate them using some of the single sign-on and in common and other kinds of frameworks that exist, and obviously hopefully make it programmable end-to-end also. It's sort of static right now, but imagine sort of the software-defined measurement monitoring framework that could be built. Hopefully we can take a crack at it. Obviously these VLAN extensions from campus to campus or from campus to remote instrumentation sites, and how to sort of do those sort of wide area, large data experiments. We could try that in GENI and then put it back on production environment. So that would be an interesting use case to try. And so I sort of gave you this example of one of the researcher use cases of where there's data and there's experimentation that GENI can facilitate. And in terms of the capabilities needs, the list from the experiments again is the same. And one of the things definitely that Marshall was talking, that GENI doesn't promise isolation, but I believe in a production system that is required as researchers use different pieces of the resource to get to different places, and they expect certain predictability, not guarantees in performance, but predictability. And so that would be interesting to see how some of the policy-directed configurations can be done to set up these programmable networks. So and again, good tools, documentation practices that will equip the performance engineer. So, so if you can imagine that role in campus in the future, I think what we could be doing in GENI is really building the tools for that performance engineer. And other challenges we'll know when we try it in the next 2 years. Thank you.
Any questions? Excellent. Thanks a lot.
Hello, I'm Ashish, and I'll be talking about some of our experiences trying to deploy programmable networking experiments on GENI and some of the challenges we ran into. Sorry. Let me start with some background. I'm a grad student at the University of Illinois, where I'm advised by Professor Brighton Godfrey. One of the themes in Brighton's research group is latency. How do you get end-to-end user latency as close as you possibly can to the speed of light? And we've been we've been trying to reduce latency at several different locations in the network stack. Some of the things that the other people in our research group have been trying to do are examples. Reducing flow setup time by combining DNS and the TCP handshake. Improving the completion time for important flows by using intelligent scheduling to prioritize those flows. Looking at the impact of things like QoS scheduling and switch scheduling and MTU and so on network performance and on latency, and several other projects. What I'll be talking about today are two techniques that I've been investigating for for controlling latency: replication and adaptation. Let me start with replication. This is something that I talked about at some length yesterday. The idea essentially is that by sending multiple copies of packets, you can reduce the variance in the delay, in the delivery time distribution. So essentially what this does is to convert some amount of throughput or capacity into a latency improvement. And this idea is applicable in several scenarios. These are just a few examples. And for each application, we were able to identify GENI resources that we could conduct experiments on to evaluate the performance of this technique. And in each case, we were able to obtain results quantifying what the performance improvement was. So this essentially is a success story. The reason this was easy to implement for us was that replication is basically a very non-intrusive technique. All you need to do is to make multiple copies of packets, which is something you can do directly at the end host, either in user space or in kernel space. So replication doesn't really require a programmable network in any meaningful sense. But the other technique we've been investigating is somewhat more complicated in terms of the support it requires from the network, and that is adaptation. Here the assumption we made was that we had a network architecture that could support sending traffic along multiple paths, and it had source routing, which means it would allow the source to pick the path that its traffic would take. So we assumed an infrastructure that supported multipath source routing. And the problem that we wanted to solve was, given that you have this infrastructure, how do you design a routing mechanism that dynamically picks the best paths to maximize the performance that your traffic sees? And the performance metric that we care about here is latency. So we came up with a set of routing mechanisms that we felt would work. And then we needed to test them in an experiment. The two requirements that we had for our experiment were, first, we needed an efficient implementation of this novel multipath source routing internet architecture. Second, we needed to have realistic background traffic, because what we wanted to test was how well we could adapt to changes in network conditions, which means that we needed to have some sort of a deployment which accurately reflected the network conditions that you would see in the internet. So we tried deploying this, and the first deployment that we tried was as a software overlay on top of Planet Lab. This directly gave us the second requirement, realistic background traffic. But because this was a software implementation running on an overlay, the implementation was not very efficient. So what we tried next was moving to an OpenFlow deployment. And when we tried running this on OpenFlow, we ran into two problems. The first was an implementation issue. What we needed here was an architecture that supported multipath source routing. And if you want to do source routing, then in general, what you need is support for arbitrary length packet headers. But we were on an OpenFlow deployment that restricted us to fixed length IPv4 packet match rules. So what we ended up doing was a sort of hack in which we used some fields in the UDP TCP header, primarily the source port, as a sort of tag to control how the traffic went along the network. But this only worked for us because we had a very small network, a very small topology with a very small number of paths. The number of paths in a network is exponential in the number of nodes that you have, so this would not scale to larger topologies. One thing that would have made a true deployment of multipath source routing possible would have been MPLS support. Now I know that the question of support for MPLS or OpenFlow 1.x in general is a fairly, well, it's just a non-trivial issue from a practical perspective. But if you happen to be keeping score, then this is one example of an, sorry. Okay. But this is one example of an application of an experiment that would have been significantly easier with that kind of support.
So specifically, make sure I understand. So specifically, I mean, what you want is not, if I understand it right, what you want is not necessarily specifically MPLS. It's you want a point-to-point link over which you have control of all of the header space.
Right.
Okay.
Right.
Of which MPLS is one way.
Right. I mean, the specific thing that we wanted to implement here was source routing. Hop by hop source routing, and I think that was I think one of the primary application scenarios for which MPLS was designed, which is why I'm talking about MPLS here. But I mean, you're right in that what we need in general is just point-to-point header modification capability.
Because the stitching stuff that was demonstrated using like Internet to ION and stuff, it seems to me would probably fill that.
I see.
And I think that there is going to be a lot more of that happening in a lot more real way in the next couple months.
Okay. Let's see. Right. So the other thing that we could have done is to directly go for a software routing implementation, but this wouldn't solve the other issue that we ran into, which was a lack of realistic background traffic. Now, so what we wanted from the network essentially was the abstraction that we wanted from the network was that we had a slice at each router. Most of the router was forwarding realistic internet-like traffic patterns, but that we had a slice at each router that was implementing our routing mechanism, and that our traffic was competing with the traffic on the rest of the internet. And the problem, if you can call it that we ran into is essentially that the OpenFlow deployment that we have in GENI right now is too well provisioned. We were seeing almost no cross traffic on either the campus links or the NLR internet to core links. And so what we wanted to test was our ability to react to network conditions, which to react to variations in path performance, which means we needed to have some level of variation in path performance in the first place. We had an undergrad student working on this who tried to artificially generate cross traffic, but he claimed he wasn't able to generate enough traffic to be able to cause to have a significant effect on the performance of the links in the OpenFlow deployment. But I mean, even if he were able to do that, there's still the problem that this would be artificial traffic. And the problem of generating artificial traffic that looks like internet traffic is still open. And this might just be a problem that goes away as the OpenFlow deployment expands. So this is one reason why I'm very interested in what's happening with the GENI rack deployment. So I mean, if you have a large-scale GENI rack deployment, then maybe the amount of traffic on the core would be large enough that we would start to see the significant amounts of the kind of variation that we wanted to see. But it's also possible that it might not. So I guess the basic problem that the general problem that I'm talking about is that we've been discussing performance isolation as a goal, but not every experiment wants performance isolation. There are some experiments, such as ours, for which it would actually be preferable to have some amounts of background traffic. And I think this is something that should be kept in mind when thinking about the provisioning of the GENI infrastructure. The other thing I was going to talk about was tooling support for tools for deployment, measurement, and instrumentation. But ours was a very simple experiment in which all the measurements that we needed to collect could be collected, or in fact had to be collected at the end host. So this is not really something I'm really qualified to comment about. So I'll just skip this and end by summarizing. These are the two issues I've talked about today. The first is support for novel internet architectures. Some of the features in OpenFlow 1.1, 1.2, and so on, such as link aggregation and MPLS, would significantly ease the deployment of some new internet architectures. Now, obviously, there are some architectures that are so novel that the only way you could possibly deploy them would be using a software routing implementation. But support for OpenFlow 1.x would expand the set of protocols or architectures that you could deploy directly on OpenFlow without having to go to a software implementation. And ours is one example of an architecture that would be possible to implement in this expanded set, but not in a fixed length IPv4 world. But then again, we are just one data point. And I realized that the question of support for OpenFlow 1.x is a fairly complicated practical issue. So this is not something that I'd stress very strongly. And the other thing that I talked about is background traffic. So we've talked about performance isolation. If not as a practical possibility, then at least as a theoretical goal, a theoretical ideal. But performance isolation is not the only form of requirement that experiments would place on the network. There are some experiments for which it would actually be preferable to have some amounts of cross traffic. And I'm not quite sure how this could be done. Maybe just research into artificially generating internet light traffic, or maybe just a large-scale GENI rack deployment and then allowing some traffic to actually, some experimental traffic to actually go over the layer 3 internet links between the GENI rack sites, instead of just having all the traffic be forced to go over the NLR internet 2 link. But this is just a requirement that I think should be kept in mind when thinking about how the GENI infrastructure should be provisioned. And well, turns out that's actually all I have. So thank you.